Hey everyone, welcome to our second lecture bite of Astronomy 236, week 11. Today we're going to be talking about exoplanet atmospheres. And this week we're really pushing into the forefront, into the cutting edge. So a lot of what I show you will be very recent results, and a lot of what I show you will be talking about where we expect to go in the future. So, the basic idea of studying the atmospheres of exoplanets is that we can learn about them in the same way as we learn about the composition of the sun. When we look at the composition of the sun, what we're really looking at is the atmosphere of the sun, because that's where the light comes from. So that's really all that we can see when we point our telescopes at the sun. And if you remember, we talked about this back in early in this course, where we learned how we learn what the sun is made of by taking a spectrum and looking for elemental fingerprints. So, in particular, we can take a spectrum of the sun, which looks something like this. And it's a black body spectrum almost because the sun is a very dense ball of gas. But superimposed on this black body are these spectral features, these little dips in brightness at certain colors of light, which correspond to transitions of different elements. These are the fingerprints that tell us what comprises the sun. If you take a really nice image of the sun, you can see that these fingerprints are everywhere. And you can get these beautiful plots of how much light there is at different colors of light. And you can see these very sharp dips in brightness corresponding to known transitions of energy levels in atoms like iron or calcium or manganese in this case. So we can take all of these together, and with a little bit of physics, as described to us by Cecilia Payne, we can take these spectra and we can turn those into relative proportions of elements. So this is something we've been doing for stars for about a century now. But what about planets? Basically, it's the same process, but it's just much, much harder to learn what a planet's spectrum looks like. The reason is when we take a spectrum of a star like the sun, all we do is we point our telescope at that star and we put the light from the star into what we call a spectrograph, which is basically a prism that splits it up into its different colors. It's a lot harder to do this for planets. Because remember, when I said that one of the ways that we could find planets is by directly taking images of them. But it turns out that taking an image of a planet like the Earth around a star like the Sun is about as difficult as finding a firefly next to a lighthouse from about 3,000 miles away. So, if we want to do this, we really need to up our game and start improving our technology so we can actually make images like this and then take spectra of these planets. One of the biggest impediments to this was Earth's atmosphere. As you recall, the Earth's atmosphere bounces around a lot, and this is due to turbulence up in the high layers of the atmosphere, winds pushing the air in different directions, causing it to be slightly different temperature and slightly different pressure, and to bend the light in slightly different ways all the time. And the result of that is that the star gets blurred out and it bounces around like this, which makes it really, really hard to see that tiny firefly right next to the star over here. But over the last couple of decades, we've developed technology to correct for this. This is called adaptive optics. And I'm showing you how it works here. You can see these little speckles blurring around. This is actually images of a star. And when you turn on an adaptive optics system, essentially what it does is it changes the shape of the mirror of the telescope just perfectly to compensate for the changes in temperature and pressure up in the atmosphere. It measures those using a laser that it shoots into the atmosphere and really, really fast, in thousandths of a second, changes the shapes of mirrors to correct for that. And once you do that, you can get this beautiful, stable looking star right here when you turn on that adaptive optics system. And over the last couple of decades, our adaptive optics systems have improved to where we can actually take images of the first planets outside of our solar system. Here's my favorite. This is a system called HR 8799, and it has 4 planets orbiting it. And we've taken observations over many years, and you can see these planets orbiting all around the star here. This black region here is what we call a coronagraph. Think of it as basically putting your thumb up to shade your eye from something really bright. Basically, you put your thumb over the star the very fancy technological thumb, and you watch these and you look for little faint speckles next to the star, and you watch them move over many years of their orbit. When you have images like this, you can now start to think about taking these planets and measuring the spectrum of their light, because we've now separated out the light of the planets over here and over here and over here from the light of the star, which is mostly blocked by this coronagraph. And when you do that with our latest instruments, you can get spectra that look kind of like this. They're nowhere near as nice as the spectra that we see for stars, especially our sun, but you can clearly see that there are dips caused by water vapor. It turns out that there's water vapor in the atmospheres of these giant super Jupiter, very massive planets. So direct imaging has been a way for us to make some of these measurements of planet atmospheres and learn what's in them. Now, unfortunately, it's still really hard to do this. We can only directly image planets that are more massive than Jupiter, and only the ones that are very young and very hot, that are still hot after having formed from accreting all of that gas together. If we want to do this for smaller stars and for smaller planets, in particular planets more like the Earth, which a lot of us are very interested in, we have to come up with a different way to do it. Now, a couple of lectures ago, I told you that most of the planets we know about, and especially most of the small planets we know about, were discovered by the Kepler mission, which uses transits to find these planets. So Kepler looks for the small dimmings of light as these planets go between their star and our line of sight and cast their shadow onto our telescopes. Is there any way that we can take advantage of this alignment so that we can measure something about the atmospheres of these planets? It turns out the answer is yes. And the trick to doing this lies in the fact that the bigger the planet is, the more light it blocks. So essentially, we can take a measurement of how much light is blocked, and we can measure from that how big the planet must be. Now, how does this have anything to do with an atmosphere? Think about it like this. This is an image of our Earth. We can see at the very edge of this image our atmosphere trailing off into space. You can kind of see this fuzzy glow at the edge of the Earth surface. It turns out that our atmosphere is not the same transparency at all different colors. So I'll show you a couple of pictures to illustrate what I mean by this. Here's an image of our atmosphere taken at a wavelength of 8.6 microns. So this is infrared light. This is the surface of our planet here. There's really not much you can see in the atmosphere. But if I were to look at a different color of light, in particular, a color of light where the molecules in our atmosphere, air, oxygen, ozone, nitrogen, have transitions. These are the wavelengths corresponding to the energy differences between different electron states in these atoms. Then when we shine light through our atmosphere, it's going to be blocked because it's going to hit those molecules and it's going to cause a transition. So here's what it looks like if we look at a wavelength with one of these transitions. Here's a wavelength where there's a transition of an ozone molecule. You can see that our atmosphere is now opaque, and you can actually see that our planet looks bigger than it did before. I'll show you that compared again. Here is an image where we don't have any atmospheric absorption. Our planet appears smaller because we don't see the atmosphere at all. But when we look at a color where the atmosphere is opaque because there's a molecular transition, our planet appears bigger. And if our planet appears bigger here, when it goes in front of its star, it will block more light very slightly and cause the transit to be very slightly deeper. This is called transit transmission spectroscopy. And the basic idea is just to measure how deep the transits are at many different wavelengths, at many different colors of light. And if you see the planet is bigger at one particular color of light, that implies that there may be a molecule that has a transition at that wavelength, that has a spectral feature at that wavelength, which is causing our planet to look bigger. So you can use this to infer what is in the atmospheres of planets if you see a planet that's larger at certain colors of light. Here's what some of the best data we have looks like. This is data of a puffy Neptune mass planet. So it's about the mass of Neptune, but it's actually quite a bit bigger. It's about twice as big as our own Neptune. And this was observed with our most powerful instrument, the Hubble Space Telescope. And this is what we see. We see these white dots here are the measurements of how much light is blocked by the planet. And what we can see is that there's this bump right here at about 1.4 microns. This is due to transitions of water. So we know that there is water vapor in the atmosphere of this Neptune mass planet light years away, because we see that it blocks a little bit more light right at the wavelength where we expect water vapor to be. So this spectrum here is almost essentially the state of the art. This is kind of the best that we can do for planets like this. But as you can tell, it's pretty noisy. This is really a field in its infancy. We're barely able to take our first steps into learning about the atmospheres of exoplanets, and we're barely able to find the first evidence of molecules in these planets. There's a long way to go before we can start to say anything confidently about what's in exoplanets, anywhere similar to what we can say about the composition of stars. How can we move forward? Where is this field going? So it turns out that the fundamental challenge to making these observations is that these are really, really precise observations. Look at how small these differences are in the transit depth. Over here, we see that where there's no atmospheric absorption, where there's no molecules that are showing transmission, that are showing spectral features, the transit depth is about 2.05%. At this peak up here, the transit depth is about 2.085%. So only 3% of 1% difference in transit depth is this large feature here. So that's an incredibly precise measurement to make. It requires us to measure these transits extremely precisely. And to do that, we need lots and lots of data. And in particular, we need lots and lots of light. It turns out that the fundamental limitation is that we just can't collect enough light with our telescopes to make these observations better. So how can we improve? A fundamental problem in doing this is that most of the planets we know about today were discovered by Kepler. But Kepler was designed in a way so that it mostly found planets around faint stars. So I'm showing just a generic star field here. And this star in the center is actually one of the stars discovered by Kepler to host planets. I believe this one actually has 6 planets orbiting it. But this star doesn't stand out. It's pretty faint. It's not even the brightest star in its nearby vicinity. If we want to be able to study the atmospheres of planets better than this, we need to find planets around stars that look less like this and more like this, the ones that are really bright, the ones that can flood our instruments with lots and lots of light, lots of photons, so we can make these extremely precise measurements. So the reason Kepler tended to focus on these faint stars is because it only observed one small patch of the sky. If you want to observe bright stars, they're scattered all around us. So if you want to look for planets around them, you need to look at all of them. You need to find which ones happen to have planetary systems that are lined up just right with our line of sight. So if you want to find planets around bright stars, you need to look at the entire sky instead of just a small patch of sky about this big. This is about the size of what Kepler was able to look at. So to fix this problem, we've built a new mission, a new planet hunter called the Transiting Exoplanet Survey Satellite. TESS is what our acronym for that survey is. So TESS is a very similar mission to Kepler. It looks for transiting planets. It looks for planets that are lined up with our line of sight so that they block their star's light. But instead of looking at one part of the sky over and over and over like Kepler did, TESS looks at all different parts of the sky. Over the course of about 2 years, TESS looked at more than 75% of the sky. TESS launched in 2018, so this is very current, very recent. It was on a SpaceX Falcon 9 rocket from Cape Canaveral. Here's what the launch looked like. I was there. It was really fun. Here's me. And this over here, that's TESS on its rocket. I highly recommend you go visit a rocket launch if you ever have the opportunity. It was really fun. And here's what the first images from TESS look like. You can see that these images have tons and tons of stars. This is a really large area of sky. This here is actually the Large Magellanic Cloud, one of the closest galaxies to our own Milky Way. And the TESS is able to look to show much, much more sky than this entire galaxy. We can just look at so much sky all at once, so we can find planets around really bright stars. So I want to show you some of the very first results that we got out of TESS after it started working. In particular, I want you to focus on this star up here in the corner. This one right here. It's behind my thing. So this star right here. This star is called Pi Mensa, and it's one of those bright stars that we really would love to find planets around. It was known back in 2002 to have a giant planet orbiting it. This planet was discovered using the radial velocity Doppler wobble technique. This planet is about 12 times the mass of Jupiter, so a really, really big planet. But when we turned on TESS, its very first science observations revealed that there was another planet orbiting this star. This planet is called Pi Mensa C, and it's only about twice the size of Earth and only about 5 times its mass. So very quickly, immediately from the very start of TESS's observations, we were finding planets around stars that look like this, these really, really bright stars that are exactly what we need if we want to be able to make better measurements of these planets' atmospheres. And over the last couple of years, 2 years now, TESS has now completed its first survey of almost the entire sky. So TESS has now looked at over 75% of the sky, and it's found lots and lots of planets. So this is an image from a paper that's not even published yet. It's just been submitted to publication and will probably be published in the next couple of months, which lists all of the planets the TESS found in its first 2 years. And this plot is showing all of these planets in comparison to planets found by other missions. So here on the y-axis is showing the brightness of the star. So higher parts of this plot, these lower numbers, are brighter stars. So the ones at the top are brighter and therefore easier for us to learn about the atmospheres of the planets orbiting them. And on the x-axis, I'm showing the radius of the planet, so how large that planet is. The two different colors are orange for planets that are probably planets that have been discovered by TESS, solid orange for planets that are confirmed to be planets that are discovered by TESS, and red and blue are planets that were discovered previously to TESS. So these are mostly Kepler planets down here. These this large sea of blue dots over here, because Kepler discovered most of the planets we know about. And these large planets here, these big planets that are larger than Jupiter, were the ones that were discovered by telescopes on the ground for the most part. TESS is discovering tons and tons of planets that are both small and bright, and therefore really interesting planets for us to look at and study their atmospheres. So over the next couple of years, we hope that we'll be able to turn all of these unfilled orange circles into filled orange circles. We'll confirm that these really are planets, and then we'll be able to study them with our powerful telescopes and learn more about the atmospheres of these planets than we could have with the planets that we knew about before TESS launched. So the other important thing that's going to happen is that we're going to have a successor to the Hubble Space Telescope. Hubble is our most powerful telescope, but it's almost 30 years old. We really would love to be able to use something even more powerful to study these atmospheres, to see these really tiny signals and figure out what the atmospheres of planets outside our solar system are made of. And fortunately, coming along is the new flagship mission by NASA, the James Webb Space Telescope. James Webb is going to essentially be a successor to Hubble. It will be much larger. So here's a comparison of the size of the James Webb mirror to a person right here, and to Hubble right here. The mirror size of a telescope is what essentially tells you how powerful it is. The bigger the mirror, the more light that you can collect, because you're taking light from all of this area and focusing it into one tiny location. So because James Webb is so much bigger than Hubble, we'll be able to make many more precise measurements with it than we were able to before. So here's an example of the kind of improvement that we expect to see when we go from the Hubble telescope to James Webb. This is a spectrum of a hot Jupiter exoplanet, so a Jupiter orbiting very close to its star, but a massive planet, taken by the Hubble Space Telescope. You can see here that the spectrum is pretty noisy, but maybe there's a bump here, and this bump here corresponds to where we expect for water to show up. So this planet likely has water vapor in its atmosphere. When we turn on James Webb, we expect that we'll be able to take data that looks more like this. So instead of just seeing some noisy data over here, we'll see this beautiful, precise data over a much larger range in colors, which will show us many more different molecules. So instead of just being able to see water, we will see molecules like titanium oxide, carbon monoxide, carbon dioxide, and we'll have much more precise data. So the amount of improvement you can get from going from something like this, data like this, to data like this will just totally change how we think about exoplanet atmospheres. And I'm sure that we're going to find tons of surprises along the way. James Webb is supposed to launch on Halloween 2021. So mark your calendars and fingers crossed for a safe launch, because when James Webb goes up and starts telling us about exoplanet atmospheres, I think it's going to totally change the game.